Hi, we are Somayeh Jafari and Efraín Palacios, and we are going to talk about timing error avoidance, Teatime. First, we will talk about motivation and background, a brief explanation regarding what Teatime is, why it emerged, and some previous concepts related to it. After that, we'll explain the operation of Teatime and present you a prototype of its implementation. Finally, we'll expose main benefits and drawbacks. The goal is improve performance of any synchronous digital system and make it adapt to variations. The most important, temperature and supply voltage variations. Normally, engineers use worst-case part specifications for system design. That means they build robust systems that are able to operate under a wide range of operating and manufacturing conditions. But since the systems usually operate under typical conditions, they generally run at a clock frequency much lower than necessary. Under normal conditions, digital systems could run much faster if one could guarantee no errors would happen. With Teatime, we can guarantee this as it allows operation at frequencies higher than maximum specified clock frequency. As we know, increasing temperature reduces mobility, and therefore IDSAT decreases, as is shown in the graph. If IDSAT decreases, resistance increases. If resistance increases, delay increases, and the maximum frequency decreases, as the following equations reflect. How Teatime works. Here it is presented the Teatime block diagram, which is formed by a tracking logic plus a safety margin delay, a toggle flip-flop, an XOR gate, a timing checker flip-flop, an up-down counter, a digital to analog converter, and finally a voltage-controlled oscillator. The tracking logic is used to mimic the worst-case delay in asynchronous systems. It's a 1-bit wide replica of the worst-case path in the system, with a slight delay added to it that provides a safety margin for the system. The toggle flip-flop at the input to the tracking logic is clocked by the system clock, changing from 0 to 1 and 1 to 0 on alternate cycles. This provides a test signal for the tracking logic during every cycle of operation and ensures that the signal tests both types of transitions. The XOR gate normalizes the test signal for the timing checker flip-flop. T1 will always change from a 1 to a 0 at the end of the cycle. If the timing checker flip-flop latches a 1, this signifies that the clock period is close to being less than the worst-case path delay, and the system decreases the clock frequency. On the other hand, if the flip-flop latches a 0, the clock period is greater than the delay through the worst-case path, and the system increases the clock frequency, improving performance. Thereby, the timing checker flip-flop output provides the command signal to increase or decrease the clock frequency by controlling the counting direction of the up-down counter.
The digital to analog converter converts the counter output to an analog voltage signal. This signal sets the clock frequency by controlling the voltage control oscillator, and the VCO output finally becomes the system clock. The prototype. It is mainly composed by the FPGA, a test computer, and a custom oscillator card with DAC and VCO. The FPGA contains the Teatime logic and a test computer. The test computer executed a small program continuously during the experiments. The test processor stores the program's result in the cache memory. After every program execution, the PC house controller checks the results, then resets the result to bad data before the next execution. The test computer system clock Normal maximum specified operating frequency is about 30 MHz. For this reason, and as we checked before, the unit could be expected to operate at this frequency under even worst-case conditions. In basic operation, this is with the FPGA's supply voltage held constant and at a room temperature, the system clock frequency rose from 25 MHz, the VCO's lowest frequency, then stabilized at about 45 MHz when the clock period varies only slightly above and below the delay through the tracking and safety margin logic. This graph shows what we said. The supply voltage varied from 2.2 to 2.8 volts, while the test computer's case temperature remained constant for each set of voltage data. Teatime adapted to the existing operating and environmental conditions and always maximized the system clock frequency with the safety margin delay. Conclusion: it increases the operating frequency of system clock until just before a timing error would occur. Improves performance. Provide adaptable frequency control for synchronous digital systems. Need more hardware than other techniques such as Razer.